Introduction to Continuous Probability Distribution. My assumption here was going to be that you covered discrete probability distributions, and I will kind of bring you back. So as you can see on the screen here, it says recall, and then it gives you these probabilities. I put a little probability B for the binomial distribution. Okay, so X is our random variable, and then you have n choose X, P to the X, 1 minus P, n minus X there. So that was our binomial distribution. So the probability of having a success, okay, or having X number of successes. And then the one just below it, okay, was the geometric distribution. Again, it's discrete, so both of these are discrete. So that's 1 minus P to the X times P. So basically, how many failures do you have before you actually have a success? So in those probability distributions, it was nice that we had basically two things happening, success or failure. So that's what we were interested in. And also our random variable took on kind of the whole number set, right? So where we just had, 0 successes or 1 success or 2 success, okay, or 3 and so on, or maybe, failures, for instance, 0 failures, 1 failure, and so on. So what we ended up having, okay, is the fact that, we had this basically, okay, to be, 0, 1, 2, and so on, okay, or we can say, our little x, okay, is an element of really just the whole numbers, and that made it discrete. Now, we knew that when we're talking about the discrete probability distributions, the summation, right, so there's summation across all probabilities. So we had summation across all the probabilities. So this is over I. So I is just, could be 0, 1, 2, and so on, and eventually ended. Okay, so this is equal to 1. So that's by definition, we know from just probability theory, okay, that if we add up all the probabilities, they're equal to 1. And now we can actually sum them up because we had them individually. And that was great. Now, if you've forgotten, binomial distribution, for example, and discrete, you want to review it, I think it's worthwhile to review all of them. Geometric, I also had the video on the hyper geometric one. I'll put a link to the binomial one, and then you can go from there if you like. So if you were thinking about this, what happened, and if we were graphing this out, so I'm going to kind of put this across, and let's say these are the probabilities, all right, that we're going to be dealing with. And then I go across so this is basically X, okay, and I'm going to shift over the 0. So let's say 0 is here, 1, 2, 3, and say that's how many we had. And then we had our probabilities here. We would draw, so, let's say this was some probability, some probability, some probability, all right? So something like that, and then we would draw these, okay, out, and then if we sum them up, okay, across here, so basically probability 0 plus probability at 1, probability at 2, probability at 3, okay, so all of this summed up to 1, right? We can just add them up. Now, what happens, okay, as you shift along here, and this random variable is not just taking on discrete values, okay, as we had there. If they're discrete values, great. We can have and continue to talk about discrete probability distribution. So how are the probabilities distributed across all the possibilities, okay, on your random variable? But your random variable in real life is not necessarily always discrete. What if it's continuous, right? Like, what if this x, okay, now all of a sudden, so our random variable that we have is actually, okay, so little x here is an element of the real numbers. So So what if it can take on many numbers? Now, where can that happen? Well, of course it can happen. What if your random variable is, let's say, wait times, right? So time is continuous. It's not just 1 or 2 or 3. Let's say if they were in minutes, it could be, 1 minute and 3 seconds, or 1 minute, 3 seconds and 45 milliseconds, and so on. So it can take on any value. So, and of course, so it could be time, it could be height, it could be pressure, right? So let's say maybe blood pressure, okay, that we have. So we can have our random variable take on anything. And then this no longer makes sense. So if we were going to talk about and try to graph this right here above and the summation across discrete values doesn't make sense. Because, this x maybe is in some interval. So maybe between, 11, okay, and 1, right? And I'm going to close this up. So here's the set of the random variable. It can take on all of these values. And now, how in the world do we talk about probability distributions when we do have a continuous now random variable to talk about? Well, it can't be like this. Certainly, because it can take on any values. And then also, how do we sum up, okay, across a continuous variable? Because now you have an infinite number, okay, of values that your random variable can take on. So we can't just sum them up individually, one by one, because there's infinitely many of them, okay? It's continuous, it's real numbers. So we do run into a problem, okay, within this. There has to be some way of doing that. Okay, so now first of all, let's say, instead, okay, I'm going to draw this out again. And I'm going to, let's say, copy this out. So I'm going to take this right here and let me copy it for the sake of illustration here. So let's make this, still a discrete. So I just want to show you the difference. And let's say what we had, our probability was uniform. So let's say this is probability. I'm going to put P bar in here. All right. And it was 0, 1, 2, still across 4 different points. Okay. So 0, 1, 2, and 3. And this is my X right there. And then it would take on. So it's uniform throughout. So the probabilities, since they have to sum up to 1, basically are 0.25 in here. Okay, if I had 4 of them, so like this, right? So I would have that. Okay, and that would have been discrete. So this is across the probabilities. But now, as I said, what if now all of a sudden, okay, this was time? Let's say maybe wait times, where you call someone or something like that. And then, by magic, okay, maybe wait times are not a good example because anyone who studied probability, okay, that has a particular model. But let's say, in a classroom you were lucky, everybody had the same height or something like that. Okay, so throughout, or maybe the blood pressure was the same. Okay, in terms of the readings in between. And now, if I would take all of this, so let me copy this and let me paste it below. If it's now continuous, okay, so it's maybe still between 0 and maybe it's still between 3, except the values can be taken on anything. So here is, some probability. I'm going to put this a different, let's put a hat here, okay, and it's from here to here, but it can land anywhere, okay, so the values that we have. Okay, so let's say, as I said, so maybe my X indeed is time, for something, maybe not wait times, but something else. And no matter what, you're going to be waiting, okay, the probability is the same for all of them across. So here, if you fell anywhere, right, so let's say if this was at 1.125, all right, and maybe this is in minutes, all right, okay, and then you reach out and you take a look at here, and then you read it out. Now, these were actual probabilities on the discrete case. Now, we can't do that on the continuous case. So I can't say that, this is still 0.25, okay? And that's the probability for each individual point. When you're talking about continuous things, you actually have to talk about intervals. So what is the probability now? What is the probability, for instance, that you fall, okay? You know, you have your x right here, and it is falling, okay, let's say between. So it's less than 2, okay, but it is greater or equal to 0. So we now talk about probabilities of intervals, no longer of individual points. And then how do we calculate those probabilities, right? How do we do that mathematically? This is no longer, so our y-axis is no longer the probability, but instead it's the probability density. Probability density. So we call that a density. It's not for an individual point, but it's the density at that particular item across. So this density, now that we're doing, so notice what we did in here. We added these up to get our probabilities, right? And then we said this is the sum across all the probabilities supposed to be equal to 1. Now, because we have a continuous variable in here, we cannot use this symbol, okay, of a sum right here, so this sigma. So instead, what we use for continuous, because it's across every single point, right? We actually use this, again, it's sum, but it's a different type of sum. So, you know, we use almost like an S, and then, you know, if you have done calculus and integration, which you may not have as of yet, you know, it'll look something like this, but it means exactly the same thing as here. And except now, so we're going between 0 and 3. So if you stem the probabilities, all right, they will equal to 1. Now, what does that mean, the summation? That summation is actually the area under, okay, this curve. So you are starting from here to here, and you are finding what the area here is, what the entire thing, because you have your density. So for this, because it's a uniform density, so this is a uniform density in here, so uniform, okay, this is actually uniform probability distribution, and it is continuous. And then this symbol right here, okay, what we're doing is we're actually finding that the probability density across, so if you take the entire interval, so all the possibilities are supposed to sum up to 1. And we do it through basically the area. So in here, the area would have been simple. You know, you're going between 0 and 3, right? So that's 3 points, okay? So the area would have been equal to, so your x, okay, over your y. So in this case, it's just a rectangle. So this is your x, so x minus 0, okay? So that's across your x. And then from here to here, okay, so whatever this might be, so we can actually find out exactly what that is. So that area across the entire thing is supposed to be equal to 1 because probabilities sum up to 1. So as you can see here, so this would have been, so this is, okay, 3, okay, this is my little p hat. So, you know, so this would have been p hat is equal to 1/3. Okay, so that would have been 1/3 as my probability distribution across the entire thing. It's uniform. But you cannot say that the probability, all right, let's say so the probability, this does no longer exist. Like, what's the probability for x is equal to 1? Okay, well, the probability, if you're thinking about an area under just 1 point, right? 1 point there is no area, right? So the area, so the x, right? How far are you moving along x is 0. So there is no area. So technically, the probability here is 0 at a particular point. But that doesn't mean that x is equal to 1 cannot happen. It can. But in the way that we define things for continuous probabilities, we actually have to talk about, okay, intervals of some kind. What's the probability okay, that in this case, let's say time is going to be less than 2 and then greater than 0. So that we can now calculate that probability. So what would that be? It would have been the area under the curve. So here, if I take this, let me copy it, let me paste it back here. So this, for the example that I just gave, so the probability is, so it's 1/3 multiplied, so notice this is from 0 to 2, so this is times 2. So the probability is 2/3 that you fall in this range. Okay, so that is, approximately 66.7% probability. So you cannot talk in terms of continuous, okay, in terms of what's the probability at one point, because mathematically that doesn't make any sense for us. But we can certainly fall into a particular range. So, one falls in that particular range, we can make the range as small as possible. So I mean, the smaller you make the range, the probabilities are going to get tinier and tinier because of the fact that you're just finding out the area under the curve. So this is a huge difference between discrete. We didn't have a probability density. We could actually identify what happens with one. So remember, let's say binomial distribution, success and failure, maybe of flipping a coin. When you flip a coin once, it's either heads or tails. So there is a probability for that one discrete case. But this does not happen for a continuous random variable within. So we need probability densities, and then we start talking about areas under the curve. And the areas under the curve could be anything. So as you draw these out, the area under the curve, maybe it's something like this. Okay, and now it would be hard to find the area under the curve because it's not uniform, right? But you can still have that kind of probability distribution. Or maybe the probability distribution, is something like this. It humps over to the right. And by the way, these actually have names, right? So these probability distributions, if something looks like this is called positively skewed, all right, where you have your unimode, so where you have just one hump, okay, uni meaning one, okay, so this, and then your tail is more off to the right, so that is positively, this is called a tail, if you ever see that, okay, skewing off. We really didn't have any tails in this uniform distribution, right? It's just uniform because it's the same throughout. This one is not the same. So it's, typically this would be, this area right here is much more likely to happen. And then it's much harder. So the probability as you go off, it's harder to happen. This one, okay, if it's more to the right, okay, again, you just have unimode here. So one mode. And then your tail is on the left-hand side. Okay, so this is, again, your tail. This is called negatively. So negatively skewed. So the word skewed means it's skewed to that right. Positively, it's skewed to the left. All right. So you can have all kinds of different probability distributions. And as you study this is just an introduction video, but you will study, one of the most common ones that students study, okay, is this one. This is kind of the normal distribution, where things are nicely evened out across some particular mean, right? So it's evenly spread out over a particular mean like that. So that would have been a normal distribution. You're going to run into that. But there are many others, okay? So if you see, maybe I'll give you, so this one, sometimes you'll see something like this. It kind of has a double hump like that. So this is called bimodal, right? So this is bimodal. And so it's called bimodal because there's two of those modes, those humps that you see there. Okay, so you might see that. So all of these probability, okay, distributions, these densities that you have, you would have to find areas under the curve to find probabilities within a range. Again, remember that, within a range for continuous, because it can take on any values. Okay? It's not discrete. where it's just on one particular point, okay, that we have, and then we can sum them up. So these ranges that you carry, okay, so within here and here, so as I said, if you find the area under this curve, you can approximate it, for instance, okay, we could have done something like this, right, and then we could have approximated something like that, and then find the areas under the curve to get, an approximation for the probability within that range between points A and B, for instance. So what's the likelihood that you fall in that range? So that's the key difference. Now, when you're studying this, at least in this chapter, as I'll be doing these videos, okay, we'll probably just be hitting the normal distribution because it's a common one which is taught in the beginning. But if you go on and carry throughout and study these continuous probability distributions, you'll run into many others as well. So that's it. That's all that I have for you, okay, for this particular introduction video. I hope that you can distinguish the difference between discrete and continuous, so those random variables, and then what happens, okay? Thanks for watching. See you in a future video. Bye, everybody.